Travel back through time, decades before your birth, and find your grandfather. Young, his whole life ahead of him, and end it before he ever meets your grandmother, erasing the chain that makes your parents and you. Now follow the logic. If he dies, you're never born. So you never build the machine, so you never travel back, so he lives, so you're born after all, so you travel back, so he dies again. The contradiction doesn't resolve. It oscillates forever between two states that can't both be true and can't both be false. For most of the last century, this was the wall. Classical physics looked at the closed loop and declared the universe would break. Then, in 1991, a physicist at Oxford named David Deutsch did something stranger than fiction. Rather than forbid the journey, he wrote the mathematics of what happens to a quantum system forced around the loop, and proved the contradiction dissolves by changing what you are. On his model, you're not the person who kills your grandfather, nor the one who fails. You exist as both at once, a 50-50 quantum mixture of the version that acts and the one that cannot. The equation doesn't break, it balances, and the price is your own continuous identity. Tonight, we examine the mathematics that turns your past into a superposition. You'll learn what a closed Timelike curve is, how Deutsch's fixed point condition forces a paradox into a stable quantum state, why the grandfather-qubit settles at exactly 1/2, and what this can and cannot tell us about determinism, identity, and why there's any structured reality for it at all. If you find value in explorations like this, consider subscribing. Now, let us begin. Start with the word itself, because the word is doing more work than it appears to. Closed Timelike curve. 3 terms, and each one carries weight. Timelike means a path through spacetime that a real object with mass could actually follow, slower than light, the kind of trajectory your own body traces from one moment to the next as you sit here. Curve means a continuous line through the 4 dimensions of space and time. And closed means the line bends back and rejoins itself. Put the 3 together and you have a world line that loops, an object moving along it, always traveling forward into its own local future, always experiencing time pass normally second by second, eventually arrives back at an event in its own past. Not a memory of the past itself as a place in space-time reached again. This isn't how the world behaves around you. In ordinary experience, the future is ahead and the past is behind, and the two never touch. The technical name for the well-behaved situation is a chronology-respecting region, a patch of space-time where cause precedes effect, and no path loops back. Almost everything we observe lives in such a region. The startling claim of general relativity is that the theory doesn't require it. Einstein's equations, the same equations that predicted the bending of starlight and the existence of black holes and the expansion of the cosmos, also permit geometries in which the chronology-respecting rule fails, geometries with chronology-violating regions where the loops exist. The mainstream position among physicists is careful and worth stating plainly at the outset. No one claims these loops are established features of the universe you live in. The claim is narrower and stranger. that the mathematics of our best theory of gravity allows them under certain conditions, and that the physical status of those conditions remains unresolved. Hold that distinction. We'll return to it many times. To see where the loops come from, we have to start with the equation that governs the shape of space-time. The Einstein field equations, written in compact form, read g mu nu plus lambda g mu nu equals 8 pi t mu nu. Spoken aloud, that is g mu nu plus lambda g mu nu equals 8 pi t mu nu. Let me unpack the symbols, because every closed time-like curve we'll discuss is born from this single relation. The term g mu nu is the Einstein tensor, which encodes the curvature of spacetime, the degree to which geometry bends away from the flat grid of everyday intuition. The term g mu nu is the metric, the object that tells you distances and durations. Lambda is the cosmological constant, a uniform term Einstein added in 1917. And T mu nu is the stress-energy tensor, which describes the distribution of matter and energy, the stuff that does the black. Bending. Read the equation as a sentence, and it says this: the way matter and energy are arranged on the right determines the way space-time curves on the left. Geometry is not a fixed stage. It responds to its contents. Here's why that matters for time travel. If geometry responds to matter, then the right arrangement of matter could, in principle, bend space-time so severely that the local sense of future and past gets tilted. Physicists picture this with light cones. At every event, a light cone opens into the future, the set of all directions a signal or an object could travel. In flat space, these cones all point the same way, neatly stacked, future always up. But strong gravity tips the cones. Near a rotating mass, frame dragging twists them sideways. And if you could tip the cones far enough, around a full loop, the future direction at the end of the journey could point back toward the past at the start. The path would close. That's the geometric heart of every model we're about to examine. Causality isn't a separate law layered on top of physics. It's a property of the shape of spacetime. And the shape is something Einstein's equations let you bend. The history of this idea is a sequence of exact solutions, each one a specific geometry that someone solved the equations to find. The first arrived quietly. In 1937, a physicist named Willem Jacob van Stockum studied an idealized object, an infinitely long cylinder of dust spinning rapidly about its own axis. Dust here is a technical term, matter with mass but no internal pressure. When van Stockum solved Einstein's equations for the space-time around this spinning cylinder, the rotation dragged the surrounding geometry around with it, and close to a fast enough cylinder, the light cones tipped far enough to permit closed, time-like paths. At the time, the result drew little attention, a curiosity about an object too idealized to take seriously. But it was the first crack in the assumption that the universe forbids loops in time. The crack widened in 1949, and this time it was impossible to ignore, because of who found it and what he said about it. Kurt Gödel, the logician whose incompleteness theorems had already shaken the foundations of mathematics, was a close friend of Einstein at the Institute for Advanced Study in Princeton. And, as a gift and a provocation, he constructed an exact cosmological solution, a model of an entire universe. Gödel's universe is rotating, spatially homogeneous, the same everywhere, and filled uniformly with matter. And it contains closed, time-like curves, not as a hidden pathology in some unreachable corner, but as a pervasive feature of the whole spacetime. Gödel wrote, in plain language that still lands like a blow, that in such a world it is theoretically possible to travel into the past. He showed that the universe he described has no global time, no way to slice it into a consistent sequence of nows that everyone would agree on. For a man who had spent his life proving what logical systems cannot do, it was a fitting discovery. A universe consistent with our best gravitational theory, in which the orderly march of time simply does not exist on the large scale. Gödel's model gave a precise relationship between the density of matter and the rate of rotation. The relation is omega equals 2 times the square root of pi g rho. Spoken aloud, omega equals 2 times the square root of pi g rho. Here, omega is the angular velocity of the matter relative to the local inertial frames, the rate at which the cosmos turns. G is Newton's gravitational constant, the same constant that appears in the field equations. And rho is the mean density of matter, how much stuff is packed into each volume of space. The equation ties a global feature, rotation of the entire universe, to a local one, the density of its contents. And notice what this already tells us, quietly, before we've argued anything. Gödel's closed time-like curves don't appear in just any universe. They require a precise global structure, an exact balance between how fast the cosmos spins and how dense it is. This is not a generic consequence of having matter and time, it's a special arrangement. What does it mean that a loop in time, the most radical break with causality our physics allows, appears only when the cosmos is balanced on one exact relation between spin and density? Keep that question in mind. We'll need it. The next major figure formalized and extended these threads. 1974, the physicist Frank Tipler published an analysis that pulled the scattered results together. Tipler examined rotating cylinders, the Van Stockham class of solutions, and stated explicitly that the rotating cylinder field violates causality. He also noted that the Kerr solution, the geometry describing a rotating black hole, contains non-trivial closed time-like lines in a region hidden deep within its interior, beyond a horizon. And Tipler did something useful for anyone trying to understand the phenomenon. He derived a threshold, a sharp dividing line. For a rotating cylinder, causality violation is avoided as long as a quantity he wrote as AR stays at or below 1/2, and it becomes possible once AR exceeds 1/2. Spoken aloud, the condition for trouble is AR greater than 1/2. In that expression, A is the angular velocity of the cylinder in geometrized units, the natural unit system relativists use, and R is the radius of the cylinder. The structure of this result is the lesson. Even in a toy model stripped to its bones, chronology violation doesn't switch on gradually or appear everywhere. It crosses a threshold. Below the line, the loops don't form. Above it, they do. The universe of the cylinder is well behaved until rotation passes one precise value, and only then does time fold back. There's a catch with Tipler's cylinder, and it's severe. The cylinder that produces the loops is effectively infinite in length, and a real object cannot be infinitely long. This is precisely why physicists treat the model as a mathematical warning sign rather than an engineering blueprint. It tells you the equations permit something disturbing under idealized conditions. It doesn't tell you any conceivable engineer could build the thing. Tipler himself, writing about the state of the subject, observed that the exact nature of the pathology was under intense debate. That phrase, intense debate, has remained the honest description of this entire field for half a century. Not closure, debate. So far, the loops have come from spinning matter, cylinders, and cosmologies. There's a second, conceptually distinct way to fold time, and it became famous in 1988 through the work of three physicists, Michael Morris, Kip Thorne, and Ulvi Yurtsever. Their starting point was the traversable wormhole, a hypothetical tunnel through spacetime connecting two separated regions, a shortcut that an object could, in principle, pass through and survive. Thorne had been drawn into the question partly by a request from the astronomer Carl Sagan, who wanted scientifically defensible interstellar travel for a novel. What Morris, Thorne, and Yurtsever showed is that if an advanced civilization could somehow create and hold open such a wormhole, the two mouths of the tunnel could be manipulated, one moved relative to the other, so that passing through would carry you not just across space, but backward through time. The tunnel becomes a time machine. They wrote that under such conditions, causality might be violatable. The phrasing was deliberately cautious, because the same analysis made clear that the scheme leans on disputed physics at every step. It requires what's called exotic matter, a form of matter or energy that violates the ordinary energy conditions, that, in a sense, weighs less than nothing, in order to hold the throat of the wormhole open against its own tendency to collapse. Whether such matter can exist in the required form and quantity is unresolved. The proposal raised deep questions about cosmic censorship, about quantum field theory in curved spacetime, about whether an averaged energy condition must hold and forbid the whole enterprise. Even the friendliest route to time travel, the elegant wormhole shortcut, rests on foundations physicists don't agree are stable. Every one of these constructions provoked the same response from a part of the physics community. This cannot be how the universe really works, and there must be some principle that prevents it. The most famous statement of that intuition came from Stephen Hawking in 1992, in a paper proposing what he called the chronology protection conjecture. Hawking asked whether causality violations confined to a finite region, a time machine built locally rather than a whole rotating cosmos, could actually form through any physical process. His analysis suggested that when you try to build such a machine, quantum effects pile up catastrophically. As the region approaches the moment of becoming a time machine, vacuum fluctuations, the restless quantum jitter of empty space, would be amplified without bound, the energy density diverging and destroying the very structure needed to close the loop. Hawking summarized the spirit of it in a line that has become famous in its own right, suggesting that the laws of physics conspire to prevent time travel and keep the universe safe for historians. Later reviews framed the conjecture more formally as the claim that whatever the final theory of quantum gravity turns out to be, it blocks the formation of macroscopic time machines. But here's the word that matters, and it's the same word Tipler used: conjecture, not theorem, not proof. Hawking's chronology protection is a proposal, a strongly motivated expectation, but it has never been established, and the reason is revealing. To prove that quantum gravity forbids time machines, you'd need a complete, tested theory of quantum gravity. No such theory exists. The mathematics needed to settle the question is the very mathematics physics does not yet possess. So, the field sits in a strange suspension. General relativity says the loops are allowed. A powerful conjecture says nature finds a way to forbid them. And the theory that would arbitrate between these two positions has not been written. What does it mean that our deepest theory of space and time permits something our physical intuition insists must be impossible, and that the question of which one wins cannot be answered with the physics we currently have? Sit with that. It is the gap in which everything that follows lives. Before we move from space-time geometry to the quantum mechanics that is the real subject of tonight's investigation, we need to be precise about what kind of problem a closed time-like curve actually creates. Because there's more than one kind, and the distinction will matter enormously. Physicists sort the paradoxes into families. The first family is the consistency paradox, and the grandfather paradox from our opening is its purest example. The structure is a contradiction. An object goes around the loop and undoes the very conditions that sent it around the loop. The Stanford Encyclopedia of Philosophy frames the canonical case as a traveler who goes back and murders his grandfather, severing the causal chain that produced the traveler. The defining feature of a consistency paradox is that the naive story is self-refuting. It can't be told without contradicting itself. The second family is different, and in some ways more haunting, because nothing in it is contradictory at all. It's called the bootstrap paradox, or the information paradox, and its signature is not contradiction, but unexplained origin. The Stanford Encyclopedia gives a clean example. A manual titled "How to Build a Time Machine" appears from nowhere. Imagine you receive such a manual from your future self. You use it to build the machine. Then, years later, you carry the manual back in time and hand it to your younger self. Where did the information come from? You didn't write it. Your future self didn't write it either, having only received it. The knowledge exists on the loop, fully formed, created by no one. It is internally consistent. There is no contradiction. Every step is possible. And yet, the information has no source. It simply is, circulating forever, uncaused. Hold this example close. We'll return to the question of uncaused things, of structures that exist without an origin, because it turns out to be the deepest question this entire subject raises, deeper than the physics itself. These two families, the consistency paradox and the bootstrap paradox, are handled differently by different models. And that's exactly why the distinction is essential. A theory that resolves the grandfather paradox may say nothing at all about where the bootstrapped manual came from. Keep both in view. Now, the classical responses. Before David Deutsch brought quantum mechanics into the picture, there was already a way to handle closed time-like curves while staying entirely within classical physics, and Deutsch's model defines itself against it. The proposal is the Novikov self-consistency principle, developed through the work of Igor Novikov, along with John Friedman, Michael Morris, Fernando Echeverria, Gunnar Klinkhammer, Kip Thorne, and Ulvi Yurtsever. In 1990, this group formulated a self-consistency condition for physical fields evolving on spacetimes that contain closed time-like curves. And in 1992, Novikov framed self-consistent evolution as the route that avoids paradox. The idea is disarmingly simple. The principle holds that the only events that can occur are events that are globally self-consistent. Anything that would generate a contradiction has, in the language of the theory, zero probability. It simply never happens. There is exactly one history, and that history is consistent by necessity. Picture what this does to the grandfather paradox. Under Novikov's principle, you can travel back, raise the weapon, aim at your grandfather, but something will always intervene to prevent the act that would erase you. The gun jams, your hand slips, a stranger bumps your arm. You discover, too late, that the man you targeted was not your grandfather after all. The principle doesn't specify which obstacle appears. It only guarantees that some obstacle must, because the alternative is a contradiction. And contradictions in this framework have no place in physical reality. The history that actually unfolds is the one out of all imaginable histories that contains no contradiction. To test whether this was a serious physical idea or just a philosopher's escape hatch, Echeverria, Klinkhammer and Thorne studied it concretely in 1991 using the cleanest possible system, a billiard ball. Picture a billiard ball rolling toward the mouth of a wormhole time machine, arranged so that the ball enters one mouth, emerges from the other at an earlier time, and travels back to strike its younger self, knocking that earlier version off course so that it never enters the wormhole in the first place. That's the grandfather paradox rendered in the simplest mechanics imaginable. A ball that prevents its own journey. The remarkable finding was this. For initial conditions that look paradoxical, there nonetheless exist self-consistent solutions, alternative trajectories in which the ball delivers itself a gentler, glancing blow, a nudge rather than a deflection, so that it still enters the wormhole and still emerges to deliver exactly that glancing blow. The paradox has an escape. The ball can be consistent. But the billiard ball study uncovered something else, something that would echo through everything that followed. For these paradoxical setups, there wasn't a single self-consistent solution. There were many, sometimes infinitely many. The classical problem of a ball near a time machine does not have one answer. It has a whole family of answers, all of them consistent, all physically allowed, with nothing in the setup to select which one actually occurs. The contradiction was avoided. But determinism was lost in the process. Ordinary classical physics promises that given the initial state, the future is fixed, one outcome calculable. The presence of a closed Timelike curve shattered that promise. The future was no longer determined by the past. It was underdetermined, multiple, ambiguous. What does it mean that removing one impossibility, the contradiction, introduced another kind of strangeness, a failure of the universe to decide what happens next? That question will return with greater force when we reach the quantum model, because there the ambiguity does not go away. It takes a new and more unsettling shape. So this is where we stand, with the stage fully set and not one claim yet tested. General relativity, through Einstein's field equations, permits geometries with closed Timelike curves. Van Stockham found one in a spinning cylinder in 1937. Gödel found a whole rotating universe full of them in 1949 and declared travel into the past theoretically possible. Tipler in 1974 sharpened the conditions and located closed Timelike lines even inside the rotating Kerr black hole. Morris, Thorne and Yurtsever in 1988 turned the traversable wormhole into a candidate time machine at the cost of exotic matter and disputed physics. Hawking in 1992 proposed that chronology protection saves the universe from all of it, but could only conjecture, never prove. And the classical Novikov principle showed that paradoxes can be dodged by demanding self-consistency, at the price of losing the single determined future classical physics was supposed to guarantee. Every one of these results is real mathematics. Not one tells us how the universe actually behaves, because not one of these objects has ever been observed. We have been reading the rulebook of a game no one has confirmed is played. Now we turn to the figure who took the whole problem and rewrote it in the language of the quantum, and made a claim more radical than any geometry, that the contradiction can be made to vanish if you're willing to let go of what you thought you were. The paper that changed the conversation has a precise title, and the title contains a detail worth getting right. It's called Quantum Mechanics Near Closed Timelike Lines, and it appeared in Physical Review D, Volume 44, in 1991. Note that David Deutsch wrote lines, not curves. The popular name for the field became closed Timelike curves, but Deutsch's own word was lines, And getting the small things right is how you keep faith with the large ones. His stated ambition was to stop treating chronology violation with the tools of classical trajectories, balls and cylinders and worldlines, and to treat it instead with the language of quantum computation and density operators. That shift in language is the entire breakthrough. Where the classical physicist asks what path the object takes, Deutsch asks what quantum state circulates around the loop. The question changes and the answer becomes possible. To follow him, you need one object from quantum mechanics, the density matrix. In the simplest version of quantum theory, a system is described by a state, a list of amplitudes that encodes everything knowable about it, what physicists call a pure state. But the world is rarely so clean. Often we have only partial knowledge, a statistical mixture of possibilities, and to describe that we need a richer object. The density matrix, written with the Greek letter rho, is that object. It captures both the pure quantum case and the mixed statistical case in a single structure. For a single qubit, it is a 2x2 array. Its diagonal entries are real numbers that must sum to 1 because they represent probabilities, the chance of finding the system in one state or the other. Its off-diagonal entries encode quantum coherence, the delicate phase relationships that make a superposition genuinely quantum rather than merely uncertain. When those off-diagonal terms are present, the system is in a coherent superposition. When they vanish, leaving only the diagonal, the system is in a classical mixture, an ordinary probabilistic blend. Hold on to that difference between off-diagonal coherence and diagonal mixture. The resolution of the grandfather paradox lives exactly in the collapse from one to the other. Now Deutsch's central move. Imagine two systems. One is the ordinary world, the chronology respecting system, everything that obeys normal time. Call its state ρ-CR. The other is the quantum system that travels around the closed timelike curve, the part that loops back through time. Call its state ρ-CTC. When the time-traveling system loops back and meets the ordinary system, they interact, and that interaction is described by a unitary operation, written U, the standard way quantum mechanics represents any reversible physical process. Here's the demand Deutsch places on the loop, and it is the keystone of the entire theory. The state that comes back around the loop must be identical to the state that left. Whatever ρ-CTC is, after it goes around, interacts, and returns to its starting point, it has to arrive as exactly the same state it began as. Otherwise, it wouldn't be a consistent loop. It would be a state that disagrees with itself. And that is precisely the contradiction we're trying to escape. Written as an equation, the Deutsch consistency condition reads ρ-CTC equals the partial trace over the chronology respecting system of U acting on ρ-CR tensor ρ-CTC followed by U dagger. Spoken aloud, ρ-CTC equals the partial trace over the chronology respecting system of U applied to ρ-CR tensored with ρ-CTC, then U dagger. Let me translate every piece into plain words. The tensor product, written with the cross symbol, means you combine the two systems, the ordinary one and the time-traveling one, into a single joint system, the way you would describe two coins together rather than separately. U acting on that joint state, followed by U dagger, is the interaction, the moment the time traveler meets the world and they affect each other. The partial trace over the chronology respecting system is the act of looking only at the time-traveling part afterward, discarding the ordinary system, asking what state the loop is left in once the interaction is over. And the equation demands that this output, the state of the loop after everything, equal rho PSPACE, the state of the loop before anything. Input equals output. The loop is a fixed point. That phrase is the soul of the model. A fixed point is a value a process leaves unchanged, a place where the machinery turns and yet nothing moves. Take the square root of 1 and you get 1. 1 is a fixed point of the square root. Fold a paper map so that one printed city lands exactly on its own name, and that city is a fixed point of the fold. Deutsch's condition says the state circulating around the closed Timelike curve must be a fixed point of the operation the loop performs on it. Feed the state through the whole cycle, the interaction, the journey around, the return, and it comes out unchanged. The traveler's history need not be a single definite story. It need only be a quantum state that reproduces itself. Now the question that decides whether any of this is more than wishful notation. Does such a fixed point always exist? Could you set up a loop so vicious, so paradoxical, that no consistent quantum state can be found, leaving the contradiction standing after all? This is where Deutsch's argument becomes genuinely deep, and where it draws, whether he named them or not, on some of the most powerful theorems in mathematics. The space of all possible density matrices for a finite quantum system has two decisive properties. It is compact, in a precise sense closed and bounded, with no edges running off to infinity, and it is convex, meaning that if you blend any two valid states, the blend is also a valid state, so the space has no holes. The operation Deutsch's loop performs is a continuous map, meaning small changes in the input produce only small changes in the output. And there is a family of theorems, the fixed point theorems, associated with the names Brouwer and Schauder, which guarantee that any continuous map from a compact convex set to itself must have at least one fixed point. A continuous stirring of a bounded hole-free space always leaves at least one point exactly where it started. Deutsch didn't write the words Brouwer or Schauder in his paper. What he did was construct the map on the space of density operators, iterate it, average the results of the iteration, and show that an accumulation point of that averaging is a fixed point. Later expositions recognize this for what it is, a fixed point argument of exactly the Brouwer-Schauder kind. And that is why the secondary literature routinely describes the Deutsch condition as secured by fixed point reasoning. The conclusion is the line to carry with you, the single most important sentence in the quantum half of this story. The model guarantees at least one self-consistent density matrix for any finite dimensional system. The grandfather paradox, in Deutsch's framework, is therefore not a problem of no solution. It is transformed into a problem of which solution. The contradiction does not survive. Something consistent always exists. Whether that something is unique and what it means are the questions that will occupy the rest of this investigation. Let us watch the machinery resolve the grandfather paradox itself, in the cleanest possible case, because the calculation is short enough to follow completely, and the result is the heart of tonight's title. We strip the paradox down to a single qubit. The chronology respecting input, the version of you that arrives intending to act, is prepared in the definite state classical logic forbids. In the notation, that is, the state 1, the qubit definitely in the state we'll call alive and acting. The qubit on the closed Timelike curve, the loop, is in some unknown density matrix. Write it generally as a 2 by 2 array with entries A and B on the top row, C and D on the bottom, where A plus D must equal 1, since those are probabilities. We don't yet know what A, B, C and D are. The fixed point condition will tell us. The interaction is the kill operation. A unitary Deutsch writes as U acting on the joint state xy gives the state x XOR y, y. Spoken aloud, U takes x and y to x exclusive or y and y. This is a controlled NOT, the most basic 2-qubit gate in quantum computing. It means this. Look at the second qubit, the one from the loop. If it is 1, flip the first qubit. If it is 0, leave it alone. Translated into the story, the version of you coming around the loop acts upon the grandfather. If the loop carries the lethal influence, the state of the world flips, the deed is done, which retroactively prevents your departure. It is the grandfather paradox encoded in a single reversible gate, the cleanest possible statement of the self-undermining act. Now apply the unitary to the combined system and perform the partial trace over the second qubit, exactly as the Deutsch condition instructs. The mathematics is direct. Tracing out the second qubit after the controlled NOT acts on the input state, one tensored with the unknown loop state, gives back a diagonal matrix with D in the upper left corner and A in the lower right. That is the output state of the loop. And the consistency condition demands that this output equal the original loop state, the array with A, B, C, D. So we set them equal. Match the entries one by one. The off-diagonal terms B and C must equal 0 because the output has zeros off the diagonal. The upper left entry A must equal D, and we already knew A plus D equals 1. Two conditions, A equals D and A plus D equals 1, force a single answer. A equals 1/2 and D equals 1/2. The unique fixed point is the density matrix, with 1/2 on each diagonal entry and zeros elsewhere, exactly 1/2 times the identity matrix. Written cleanly, rho CTC equals I/2. Spoken aloud, rho CTC equals 1/2 times the identity. This is the maximally mixed state, the most uncertain state a qubit can be in, an even 50-50 balance with no quantum coherence at all. Read what just happened, because this is the moment the title of tonight's video comes true. The paradox demanded a contradiction, a state that is both alive and dead, both having acted and having failed, with no consistent value. The classical mind hits that wall and the universe breaks. Deutsch's condition does not hit the wall. It finds, sitting quietly in the space of density matrices, a single, self-consistent state. And that state is the perfect 50-50 mixture. In the model, the qubit going around the loop is neither definitely the version that acts, nor definitely the version that fails. It is exactly half of each. And that mixture, fed through the kill interaction and around the loop, reproduces itself perfectly. The contradiction is gone, not because the journey was forbidden, but because the traveler is no longer a single, definite thing. You would exist in this resolution as a 50-50 quantum mixture of the self who caused the event and the self who did not. The equation balances. And it balances by dissolving the one assumption the paradox depended on, the assumption that there is a single, definite, continuous you to be either alive or dead. What does it mean that the mathematics can save the universe from contradiction only by refusing to let you remain one person? I want to pause on a subtlety here, because it will matter greatly later. That 50-50 result is a mixed state, the diagonal matrix, not a pure superposition with its coherence intact. The distinction is real. A pure superposition would carry off-diagonal terms, genuine quantum interference between the two possibilities. The fixed point of the grandfather qubit has those terms forced to zero. It is a classical-looking probabilistic blend dressed in quantum clothing. So, when the popular phrasing says your past becomes a superposition, that is the loose, accessible language. The precise statement is that your past becomes a maximally mixed state. What that mixed state means, whether it describes one person who is genuinely both, or two separate branches, each containing a different definite person, or merely a bookkeeping device with no person in it at all, is not answered by the equation. The mathematics produces the matrix. The interpretation of the matrix is a separate and far more contested question, and we'll return to it. Mark this as the first seed. The equation gives an answer whose meaning it does not give. Deutsch was aware that the uniqueness we just found in the grandfather case is a special blessing, not a general rule. For other interactions, the fixed point condition does not single out one state. It permits many. Consider a setup where the input is classically consistent rather than paradoxical. Then, Deutsch showed, any diagonal state of the form p times the state 0 plus 1 minus p times the state 1 satisfies the consistency condition for every value of p between 0 and 1. An entire continuum of solutions, infinitely many consistent histories, with nothing in the equation to choose among them. We met this ghost already in the classical billiard ball study, and here it returns inside the quantum theory. The contradiction is avoided, but uniqueness is lost. To handle the multiplicity, Deutsch proposed an additional rule, and the fact that he had to propose it rather than derive it is one of the most important facts in this entire subject. He suggested that when several fixed points exist, the physically correct one is the state of greatest entropy compatible with the initial data. Entropy here is the von Neumann entropy, the quantum measure of mixedness or disorder, written S of rho equals minus the trace of rho times the logarithm of rho. Spoken aloud, the supplementary state is the one that maximizes the entropy S of rho, where S equals minus the trace of rho log rho. Applied to that continuum of solutions parameterized by P, the rule selects P equals 1/2, the most mixed of all the available states. It restores uniqueness. But here is the point that cannot be emphasized enough, and that we'll hold up to the light later. The maximum entropy rule is not forced by the fixed point equation. It is an extra assumption boated on from outside to fix a problem the core theory does not solve on its own. The consistency condition gives you a set of solutions. Selecting one requires a second independent decision. Deutsch's model in its full form is not one rule but two, and the second is a choice, not a consequence. Keep that number 1/2, and keep that fact that it had to be chosen rather than derived. We'll need both. Deutsch's framework had other features that made it the centerpiece of the field for decades. One concerns the second law of thermodynamics. You might worry that closed time-like curves, by tangling past and future, would wreck the orderly increase of entropy that governs the ordinary world. Deutsch argued the opposite, that even under chronology violation, his model preserves a thermodynamic constraint: the entropy of the output, at least the entropy of the input. The arrow of time bends, perhaps, but in his accounting it does not snap. The feature that drew the most intense attention came from computer science, and it is genuinely staggering. If you could build a computer with access to a closed time-like curve, how powerful would it be? Dave Bacon showed, in work around 2003 and 2004, that the nonlinearity inherent in Deutsch's model could be exploited to solve NP-complete problems efficiently, the notoriously hard puzzles at the heart of computer science, the traveling salesman, and the satisfiability problem, and thousands of others, for which the best-known methods take time that explodes exponentially with the size of the input. Then came the sharper, definitive theorem. In work spanning 2008 and 2009, Scott Aaronson and John Watrous proved that a computer with access to a closed time-like curve in Deutsch's framework has exactly the power of the complexity class P-SPACE. And remarkably, this is true whether the computer is classical or quantum. Their result is written: BPP with CTCS equals BQP with CTCS equals PSPACE. Spoken aloud, BPP with closed time-like curves equals BQP with closed time-like curves equals PSPACE. Unpack what that string of letters destroys. BPP is the class of problems an ordinary randomized computer can solve efficiently. BQP is the class an ordinary quantum computer can solve efficiently. And the entire promise of quantum computing rests on BQP being strictly larger than BPP, on quantum machines doing things classical ones cannot. P-SPACE is a vastly larger class, the set of all problems solvable with a reasonable amount of memory regardless of how much time they take, believed to dwarf both BPP and BQP. Aronson and Watrous proved that once you grant access to a closed Timelike curve, the distinction between classical and quantum simply evaporates. Both leap all the way up to P-SPACE. The advantage of quantum over classical, the foundation of an entire field, vanishes. A time loop wouldn't give you a better computer. It would give you a categorically different kind of computation, one that treats space and time as nearly interchangeable resources. The result is mathematically beautiful and, taken as a claim about physical reality, deeply alarming, because computational miracles on this scale are exactly the kind of thing that suggests something in the premises is too strong to be true. And note the words with which Aronson and Watrous open their analysis. They concede that closed Timelike curves are, in their phrase, not known to exist. The most powerful computational result in the field rests on an object no one has ever found. What does it mean that a model becomes most powerful exactly where it becomes least believable? That alarm has a name, and following it leads us to the criticisms, the places where the elegant structure begins to strain. We are still presenting rather than prosecuting, but a faithful presentation of Deutsch's model has to include the serious objections raised by serious physicists, because those objections are part of the scientific record. There are 4 major ones, and each exposes a different soft spot. The first objection is non-linearity. Ordinary quantum mechanics is linear, a property so fundamental it is easy to forget it is there. Linearity means that if you have a mixture of states, you can evolve each component separately, combine the results, and get the right answer. It is the mathematical backbone that makes quantum probabilities behave. Deutsch's model breaks linearity. Because the fixed point state, ρ-CTC, depends on the input, ρ-CR, the effective operation on the ordinary system is non-linear, a fact Deutsch himself emphasized. Once a theory goes non-linear, the treatment of mixtures becomes treacherous. In 2009, Charles Bennett, Debbie Leung, Graham Smith and John Smolin published a pointed critique, arguing that many of the most dramatic claims about Deutschian closed Timelike curves, the perfect state discrimination, the impossible speed-ups, depended on a specific error they named the linearity trap. The trap is this. To compute what the model predicts, researchers would take a mixed input, evolve each pure component through the nonlinear dynamics separately, and average the results as if linearity still held. But in a nonlinear theory, that step is illegitimate, because the whole does not equal the sum of its parts. Bennett and colleagues argued that the ambiguity in how you describe a mixed state makes many of the celebrated results ill-defined. Their critique didn't erase every result in the field, but it permanently raised the bar. After the linearity trap was named, no one could claim an operational miracle from a Deutschian loop without first proving they had not fallen into it. The second objection is non-uniqueness, and we've already seen its face. The fixed point equation often has many solutions. Deutsch's maximum entropy rule is one proposed way to choose among them. But the later literature treats that rule as exactly what it is, an extra assumption rather than a consequence of the consistency condition. This matters enormously for any grand claim, because resolving the paradox, showing a consistent solution exists, is a far weaker achievement than determining the future, showing which solution occurs. In many cases, the real situation is not contradiction, but multiplicity. The model does not tell you what happens, it tells you what could happen, and hands you a separate rule, justified separately, to pick. A theory that needs a second principle to say what it predicts is a theory whose predictive core is incomplete. The third objection is discontinuity, and it cuts against the very thing the model was praised for. Deutsch's framework was celebrated as a smooth resolver of paradoxes. But in work around 2009 and 2010, the physicists de Jong, Fry and Imbo showed that the model can make its output a discontinuous function of its input. A tiny, infinitesimal change in the state you feed in can produce a sudden, finite jump in the state that comes out. And they showed these discontinuities persist even under natural attempts to modify the model to remove them. For a theory advertised as bringing smooth consistency to the chaos of time travel, built on a fixed point argument that assumed continuity, the appearance of genuine discontinuities in the predictions is a serious internal pathology. The smooth resolver is not, on closer inspection, entirely smooth. The fourth objection is the most philosophically corrosive, and it comes from recent and rigorous work. It asks whether the Deutsch condition is even about real closed time-like curves at all. The physicists Tolksdorf and Verch, working in algebraic quantum field theory, showed that the Deutsch consistency condition can be fulfilled, at least approximately, even on perfectly ordinary spacetimes that contain no closed time-like curves whatsoever. The well-behaved, causally orderly geometries called globally hyperbolic. And in work published in 2021, they showed the condition is generically fulfilled in classical statistical systems under broad assumptions, systems with no time travel anywhere in sight. Their warning is unusually direct for a physics paper. They caution that taking the Deutsch condition as characteristic of real closed time-like curve physics could be misleading and should be handled with caution. The force of this is hard to overstate. If a condition meant to capture the essence of time travel can be satisfied where there is no time travel, then the condition may not be telling you about time travel at all. The bridge from Deutsch's elegant little quantum networks to bold statements about loops in the fabric of reality is far shakier than the popular accounts suggest. What does it mean that the equation said to capture time travel can be satisfied in a universe where time travel does not happen? And the empirical situation closes the case for honesty. No experiment has confirmed a real Deutschian closed time-like curve. There has been laboratory work that draws on the model. In 2014, Martin Ringbauer and collaborators performed a photonic experiment, and the verb in their own abstract is the one that matters. They write that they experimentally simulate the nonlinear behavior of a qubit interacting with an older version of itself. Simulate. They built an optical system that mimics the mathematics, that reproduces the input-output relations Deutsch's model predicts, using ordinary photons and ordinary quantum optics, with no actual time travel anywhere in the apparatus. It is a demonstration of the model's logic, not an observation of the model's reality. A flight simulator reproduces the behavior of an aircraft without ever leaving the ground. The Ringbauer experiment reproduces the behavior of a time loop without bending a single instant of time. That is the present factual baseline, and it deserves to be stated without flinching. The mathematics is real. The theorems are real. The object the mathematics describes has never been shown to exist. There is a competing model we have to place beside Deutsch's, because its existence is itself a major fact. In 2011, Seth Lloyd and a team of collaborators proposed an entirely different quantum theory of time travel, the post-selected closed timelike curve, or P-CTC. Where Deutsch's D-CTC uses a fixed-point density matrix, the post-selected model uses a different mechanism drawn from quantum teleportation and a path integral picture that enforces self-consistent histories. The technical details matter less for our purposes than the single devastating fact Lloyd and his co-authors stated plainly. Their model is physically inequivalent to Deutsch's. Given the same time travel scenario, the two theories make different predictions. They are not two descriptions of one underlying physics. They are rival physics, both from serious researchers using legitimate quantum mechanics. So the field doesn't even possess a single agreed-upon toy model of quantum time travel. It possesses at least two, and they disagree. Pressed on the grandfather paradox, the D-CTC says you become a 50-50 mixed state, while the P-CTC resolves it through post-selection, suppressing the inconsistent histories by a different route entirely. The post-selected model has its own internal disputes, which only shows how unsettled all of this remains. Also in 2011, the physicist Timothy Ralph argued that the post-selected teleportation approach allows signaling to times before the closed timelike curve was even created, and allows information paradoxes to form. Lloyd and his co-authors replied almost immediately that Ralph's construction had neglected necessary interactions, and that a fuller analysis removes the difficulty. The point is not to adjudicate that exchange. The point is that here is a live, unresolved dispute happening entirely inside the time travel literature. Physicists arguing about which quantum model of time travel is even self-consistent. This is not a fight between physics and outsiders. It is the field arguing with itself in real time about its own foundations. Now we arrive at the three implications the model has been made to carry in popular discussion, and faithful presentation requires laying them out neutrally while marking carefully exactly how far the physics actually reaches. These are the doorways through which the deepest questions enter, and later we'll examine what tries to come through them. The first is determinism and free will. The naive intuition runs that a closed, time-like curve must annihilate free will, because if the loop demands consistency, the traveler is compelled, forced, to fail whenever success would breed contradiction, a puppet of the geometry. But the actual literature is subtler, and the subtlety runs the opposite way from what people expect. The Stanford Encyclopedia summary and the careful classical analyses emphasize that closed time-like curve spacetimes more often produce underdetermination, multiple self-consistent solutions than a single fatalistic script. Remember the billiard ball with its infinite family of consistent trajectories? The problem is usually not that the future is rigidly fixed. It is that the future is not fixed enough, that the physics permits many consistent continuations and selects none. So the honest situation is genuinely mixed. Deutsch's model can look deterministic when a unique fixed point exists, as in the grandfather-qubit. Underdetermined when many fixed points exist, and under the many worlds reading, it takes yet another form entirely. There is no consensus formula that turns closed time-like curves into a clean theorem about whether the will is free or bound. The popular claim that the physics settles the free will question in either direction outruns what the physics actually delivers. The second implication is the many worlds interpretation. And here we must be exact, because Deutsch himself was a committed advocate, and his paper is explicit about it. Deutsch favoured an Everettian reading of his model, named for Hugh Everett, who in 1957 proposed that the quantum wave function never collapses, and that all outcomes of every quantum event are equally real, each in its own branch of an endlessly splitting reality. Deutsch wrote that chronology violations would produce experimentally detectable differences between interpretations of quantum mechanics, described the paradox resolution branch-wise in multiple universe language, and made the striking claim that closed time-like lines would provide what he called gateways between Everett universes. On this reading, the grandfather paradox becomes almost intuitive. The older traveller does not return to the same branch from which the younger traveller departed. He emerges in a different branch. In one branch, the grandfather dies, and that branch simply contains a world in which this particular traveller was never born there. In another, the grandfather lives and produces the traveller who left. The contradiction dissolves because it is spread across branches rather than crushed into a single history. The 50-50 mixed state is then read not as one person who is somehow both, but as a description of two branches, each housing a definite outcome. But the word that governs this whole picture must be stated and underlined, and it is the same kind of word we kept finding earlier: interpretation dependent. The many worlds reading is not a result of the equations. It is a way of reading the equations, one of several, and it is not universally accepted. To buy Deutsch's branch transfer resolution, you have to buy two separate things at once: the P-CTC model and the Everettian interpretation of quantum mechanics, and neither is established fact. The mathematics produces a density matrix. Whether that density matrix testifies to a multiplicity of equally real worlds, or merely to our ignorance within a single world, the mathematics does not say. Deutsch read it one way. The reading is a philosophical commitment layered on top of the physics, not a discovery forced by it. We'll return to what rides on that commitment. The third implication is the most personal and the most fraught, and it travels under the names quantum suicide and quantum immortality. The physicist Max Tegmark popularized a thought experiment called quantum suicide, tied to the many worlds interpretation. The reasoning, briefly and with all the caution such reasoning deserves, runs that if every quantum outcome is realized in some branch, then in any situation that would kill you based on a quantum event, there is always some branch in which, by chance, you survive. And since you can only ever find yourself in a branch where you are alive, to find yourself anywhere would subjectively experience never dying. From this, some have drawn the conclusion called quantum immortality, the claim that consciousness, threaded along the branches where it persists, never experiences its own end. Stated plainly, and the seduction is obvious, and so is the danger. The physics community's response is the part that gets lost in popular retellings, and it is essential. The move is widely regarded as a fallacy. The physicist Jacques Mallat, among others, argued in detail that the inference from many worlds to quantum immortality does not follow, that it rests on a confused treatment of probability and personal identity, on quietly assuming exactly what it sets out to prove. And here is the detail that should give everyone pause, because it comes from the model's own architect. David Deutsch himself, the very physicist whose mathematics we have spent this entire investigation following, rejected the probabilistic move at the core of quantum immortality. The move that says a rational observer should simply ignore the branches in which they die. The man who built the fixed point model, who championed the many worlds interpretation more vigorously than almost anyone alive, did not endorse the leap to immortality. So the precise statement, the one that survives scrutiny, is this: nothing in Deutsch's 50-50 mixed-state grandfather-qubit by itself establishes immortality, or guarantees survival, or settles the question of what a person is. The equation gives a density matrix. It does not give a doctrine of the soul, or a promise that you cannot die, or even a clear account of who the you in the equation refers to. Those are additions. Every one of them is contested. And mark this as the deepest seed of all, the one we'll finally harvest. The model describes a 50-50 state, and then falls silent on the only question that makes that state frightening, which is whether there remains, through all the branching and looping, a real and continuous you to whom any of it happens. That is the full architecture of Deutsch's closed time-like curves, presented as faithfully as I can manage, with every strength stated and every soft spot marked. The fixed point condition that always finds a consistent quantum state. The grandfather-qubit settling at exactly 1/2, the maximally mixed state. your past rendered as a 50-50 balance. The maximum entropy rule added by hand to choose among solutions. The P-SPACE computational power that should make us wary. The serious objections of nonlinearity, non-uniqueness, discontinuity, and the warning that the condition may not even be about real time travel. The rival P-CTC model that disagrees with Deutsch and with itself. And the three great implications: determinism, many worlds, and quantum immortality, each of which, examined closely, reaches beyond what the equations can carry. Every claim in this part was presented in the spirit of a reporter, and nothing was yet tested. That changes now. For the past hour and more, I have laid out what the mathematics says and what physicists claim it might mean. Now we stop presenting and start examining. Because woven through everything we have covered is a set of larger claims that go past the physics into metaphysics. Claims some have used to argue that this mathematics dissolves not just the grandfather paradox, but the need for any deeper explanation of reality at all. Those claims deserve a fair hearing and a hard test. Let us give them both. For the past 2 hours, I have presented Deutsch's closed Timelike curves the way a reporter presents a story, and debunked nothing. That was deliberate. I wanted the model to stand at full strength before we tested it, because a fair test begins with a fair hearing. Now the hearing is over, and the examination begins. We are not going to attack the physics. The physics is real, the theorems are sound, and the fixed point condition does exactly what Deutsch showed it does. What we are going to examine are the larger claims hung on this physics, the metaphysical conclusions some have drawn from it, the assertions that this mathematics removes the need for any deeper explanation of why there is a structured reality at all. Those claims are not physics. They are philosophy, wearing the borrowed authority of an equation. And when we hold them up to the light, one by one, they do not survive. 3 claims in particular have grown up around this subject, and each deserves a fair statement, a careful cross-examination, and an honest verdict. The first is that self-consistent causal loops remove the need for any first cause. The second is that Deutsch's resolution shows contradiction dissolving on its own, so no transcendent order, no designer, no foundation beyond the equations is required. The third is that a 50-50 superposed self proves there is no real, continuous you, and with it, no soul, no enduring person. We take them in turn. Begin with the first and most ambitious claim, the one that reaches furthest. Some who encounter the bootstrap paradox, the manual that appears from nowhere and circulates forever with no author, draw a sweeping conclusion. If information can exist on a loop with no origin, they argue, if a self-consistent cycle can sustain itself without anything outside it, then perhaps the universe itself is such a loop. Perhaps existence bootstraps itself into being, a self-causing cycle that needs no first cause, no eternal foundation, no creator. The closed Timelike curve becomes, in this telling, a model for a self-explaining cosmos. We should state it at its strongest before we test it. The strongest form runs like this. Causation, as we know it, may be a local feature, not a global necessity. If time can loop, then the demand that everything have a prior cause may simply be a parochial prejudice, true in our corner of space-time, but not binding on reality as a whole. The loop is its own explanation. Now cross-examine it. The first question to ask any explanation is what it actually explains and what it quietly assumes. So look at what Deutsch's model presupposes before it can resolve a single paradox. To write down the fixed point condition, you need a spacetime, a four-dimensional manifold with a metric that tells you intervals and durations. You need the structure of quantum mechanics, the space of density matrices, the rules of unitary evolution, the partial trace. You need an interaction, the unitary U, specified and given. You need the entire apparatus of fixed-point mathematics, the compactness and convexity of the state space, the continuity of the map, the theorems that guarantee a solution exists. The loop does not produce any of this. The loop operates inside all of it. Deutsch's model describes what happens to a quantum state given a spacetime, given the laws of quantum mechanics, given an interaction, given a state space with exactly the properties that make a fixed point inevitable. Strip those away, and there is no loop, no fixed point, no resolution, nothing. The self-consistent cycle is not self-sufficient. It is one of the most thoroughly dependent structures in all of physics, leaning at every point on a framework it did not create. This is the cosmological argument, and the closed Timelike curve does not escape it. It walks directly into it. The argument is old and simple and has never been answered. Nothing comes from absolute nothing. Absolute nothing, true nothing, no space, no time, no matter, no energy, no laws, no quantum fields, no fixed-point theorems, no potential of any kind, has no power to produce anything, because there is nothing there to do the producing. 0 plus 0 is 0. If there were ever absolute nothing, there would be absolute nothing still, forever. But there is not nothing. There is a structured reality of extraordinary mathematical richness, rich enough that closed Timelike curves and density matrices and fixed-point conditions are even definable within it. Therefore, something has always existed. That conclusion is not a leap of faith. It is forced. The only question that matters is what that something is. Is it unconscious matter or an intelligent cause? And here the loop offers no help, because a loop is not a foundation. A loop is a pattern a foundation permits. You cannot bootstrap the foundation itself. The manual that appears from nowhere is internally consistent, yes, but its very strangeness is precisely that information seems to exist without a source. And we recognize that as a paradox, a thing that should not be, rather than as a model for how being works. The bootstrap paradox does not show that uncaused existence is natural. It shows that uncaused existence is so deeply contrary to reason that we flag it as a paradox the moment we meet it. What does it mean that the human mind recognizes a thing with no origin as a problem to be solved, rather than as the way reality simply is? There is a sharper way to put the failure of this first claim, and it comes from turning the argument around on itself. The whole appeal of the self-consistent loop is that it is rigid, that the fixed point condition forces the state into exactly one self-consistent form. But rigidity is the opposite of self-explanation. A thing that must take a precise mathematical form is a thing governed by a law, and a law is not nothing, it is a structure. And structure is exactly what cries out for explanation. Deutsch's model does not show contradiction dissolving into chaos. It shows contradiction resolved by the imposition of an exact, demanding mathematical constraint. The grandfather paradox is not removed by letting anything happen. It is removed by forcing the loop state to be the one precise density matrix that reproduces itself, and where even that is not unique, by adding a second exact rule, the maximum entropy selection, to pin it down further. This is the second claim, the assertion that Deutsch shows order emerging from nothing, and it collapses on contact with the actual mathematics. The model is not an argument that explanation has reached bedrock. It is one of the most vivid demonstrations in modern physics that even the most exotic corner of reality, even time folded back on itself, is shot through with precise, rigid mathematical order. And order is the signature of mind, not its absence. Consider what we found earlier, the precision required for the loops to exist at all. And notice that we are now harvesting a seed planted long ago. Gödel's closed timelike curves do not appear in any universe with matter in it. They require an exact relation between the density of matter and the rate of cosmic rotation. Omega equals 2 times the square root of pi g rho, a precise global balance. Tipler's rotating cylinder does not violate causality at any old speed. It crosses the threshold only when the quantity AR exceeds exactly 1/2. The wormhole time machine of Morris, Thorne and Yurtsever does not form from ordinary matter. It demands exotic matter with properties no one has confirmed can exist. And Deutsch's quantum resolution does not arise in a formless void. It requires the compact convex state space, the continuous map, the fixed point theorems, the specified interaction. At every level, from the largest cosmological solution to the smallest qubit, chronology violation is not the effortless, automatic consequence of just matter and just time that the popular telling implies. It is a knife-edge phenomenon, balanced on precise conditions defined within rich mathematical structure. Picture a locksmith examining a lock of extraordinary precision. A mechanism where dozens of tumblers must align to within a hair for for the bolt to move. He can describe every spring, every pin, every tolerance. But the precision itself, the fact that the mechanism is built to such exacting specification, is not explained by describing how it works. Precision points beyond the mechanism to the decision that set the tolerances. What does it mean that the most exotic possibilities in physics, the loops in time themselves, turn out to require not less order than ordinary reality, but more? Precision requires decision. That is the part that stays with me. Not the strangeness of the loop, the exactness of what the loop demands. Now the third claim, the most intimate one, the one that touches the title of this video and the place where the whole subject becomes personal. The claim is that Deutsch's grandfather-qubit, settling into its 50-50 mixed state, proves there is no real, continuous you. If the self who travels back is neither the one who acts nor the one who fails, but a balanced quantum mixture of both, the argument goes, then the very idea of a single, persistent person, an enduring I, is exposed as an illusion. There is no soul, no continuous self, only states and probabilities and density matrices. We are bookkeeping objects, the argument concludes, and the equation proves it. This is the claim that the model dissolves the self. Give it its fair hearing. The intuition behind it is not stupid. The 50-50 mixed state really does describe something that is, in a precise mathematical sense, not a definite single thing. The qubit on the loop is genuinely half one outcome and half the other. And if a person could be reduced to such a state, personal continuity really would be in trouble. The claim has the form of a serious argument, and it deserves a serious answer rather than a dismissal. So, cross-examine it and watch where it fails, because it fails at the exact point we marked twice in the earlier parts and promised to return to. Recall the first seed. The equation produces the density matrix, but it does not tell you what the density matrix means. Recall the deepest seed. The model describes a 50-50 state and then falls completely silent on the only question that makes that state frightening. The question of whether there remains a real, continuous you to whom the state belongs. This is not a gap I am inventing to rescue a conclusion. It is a gap the physics literature itself acknowledges, openly and repeatedly. The research is explicit that a Deutschian mixed state is not automatically a story about an enduring subject who experiences both branches. To get from the matrix to any claim about personal identity, you need extra metaphysics, additional assumptions about what a person is, about measure, about which branch owns the self, about what survives and what does not. And those extras, the literature states plainly, are not settled by the equations. They are not in the physics. They are imported from outside, and they are contested. So, watch what the third claim actually does. It takes a mathematical object, the density matrix, which is silent on the nature of the self, smuggles in a philosophical conclusion that there is no enduring self, and then credits that conclusion to the equation. But the equation said no such thing. It produced a matrix and stopped. The denial of the continuous self was added by hand, exactly the way the maximum entropy rule was, a separate decision dressed up as a discovery. And here the argument does something worse than overreach. It defeats itself. Ask who is doing the reasoning. Ask who follows the derivation of the grandfather-qubit, who grasps that the off-diagonal terms vanish, who draws the inference that the self is therefore an illusion. A continuous, reasoning subject does all of that. A single mind holding the premises together across time and arriving at a conclusion. If there were genuinely no continuous you, there would be no one to follow the argument from beginning to end. The claim that there is no continuous self can only be asserted by a continuous self. It saws off the branch it sits on. The subjective I, the awareness that observes the thoughts and persists through the reasoning and notices that it persists, cannot be located in any density matrix, because the density matrix is an object that this very awareness contemplates. The thing doing the looking is not among the things it looks at. Think about it from a different angle, because this point is the hinge of the whole video. Neuroscience can correlate brain states with mental states, and physics can correlate a quantum system with a density matrix. But a correlation is not an identity, and it is not an explanation. Matter, on its own terms, is not conscious. Arrangements of unconscious particles do not become aware simply by being arranged. And arrangements of probabilities in a 2x2 matrix do not become a self simply by summing to 1. There is a hard problem here that no equation in this entire subject touches. The problem of why there is something it is like to be you at all. Why there is inner experience rather than mere mechanism. Deutsch's model, for all its power, operates entirely on the outside of that problem. It says nothing, can say nothing, about the experiencing subject for whom the question of survival, of continuity through the loop, would even matter. The 50-50 state is frightening only if there is a you to be frightened. And the existence of that you is precisely what the equation presupposes and never produces. What does it mean that the most physics can offer about the self is a matrix that is silent about the very thing we most want to know? It means the self was never inside the physics to begin with. It was always the one standing outside, reading it. There is a fourth move that holds all three of these failed claims together, and it must be named because it is the master argument of the secular reading of this entire subject. It is the move that says, we do not have the full answer yet, but the trajectory of physics is clear, and eventually the equations will explain everything, including the loop, including the self, including why there is something rather than nothing. Closed, time-like curves are just one more frontier, and the frontier always falls. Give it time, and the gaps will close, and no first cause, no foundation, no mind behind it all will be needed. This is the promise that the future will tidy everything away. Examine that promise against the actual state of this field, because this subject, of all subjects, is where the promise is most thoroughly refused by the evidence. What does the literature on closed time-like curves actually contain? Not a march toward closure, an ever-deepening set of disagreements. We do not have one quantum theory of time travel. We have at least two: Deutsch's DCTCs and Lloyd's P-CTCs, physically inequivalent and contradicting each other. And the P-CTC camp could not even agree internally. The uniqueness of Deutsch's fixed points is not guaranteed, and the maximum entropy rule used to restore it is an extra assumption no one derived. The predictions can be discontinuous. Hawking's chronology protection conjecture remains unresolved after 3 decades and cannot be resolved without a theory of quantum gravity that does not exist. And Tolksdorff and Versh warn that the central condition may not even describe real time travel at all. Not one observation establishes that a real closed time-like curve exists anywhere in the universe. The laboratory work simulates the model. It does not find the object. This is not the profile of a frontier about to fall. It is the profile of a question growing more tangled the harder it is pressed. To stand in front of this landscape and say, "Science will surely explain it all away," is not a conclusion from the evidence. It is faith. Faith in a future that the present actively contradicts. And this is not a failure of science. Science is doing exactly what it is built to do, describing how the structures of reality behave with precision. What it was never built to do is explain why there are any structures to describe. That is not a defect in physics. It is the boundary of physics. The question of why anything exists at all is not a scientific question with a delayed answer. It is a different kind of question, and it has a different kind of answer. Let me draw the cross-examinations together because they converge, and the convergence is the verdict. Each of the 3 claims fails in the same way. The claim that the loop removes the need for a first cause fails because the loop presupposes the entire framework it pretends to explain. The claim that contradiction dissolves on its own fails because the dissolution is achieved by imposing rigid mathematical order, and order is not the absence of a foundation, but the fingerprint of one. The claim that the 50-50 self abolishes the soul fails because the equation that produces the mixed state is silent about the self and can only be contemplated by the very self it is said to abolish. In every case, the pattern is the same. A piece of genuine mathematics, real and sound, is asked to carry a metaphysical conclusion it cannot support, and the conclusion is smuggled in from outside and then attributed to the math. Strip away the smuggling, and what the mathematics actually shows points the other way entirely. It shows a reality saturated with precise structure, governed by exact law, defined within a rich and dependent framework. Contemplated by conscious minds, the framework cannot explain. Picture a detective who arrives at a locked room and finds a finely machined apparatus running through a flawless, self-consistent cycle, every gear meshing, the whole mechanism humming in perfect closure. The naive observer says, "Look, it runs itself. It needs no maker." The detective asks the better questions. Who cut the gears to such tolerance? Who chose the laws the gears obey? Who set the machine where a mind could find it and understand it? The self-running cycle is the strongest evidence in the room that someone built it to run, because nothing assembles itself to that precision by no one's hand. A fixed point is not the same thing as an explanation. A loop that closes is not a foundation that stands. The mathematics balances, and the deeper question survives, untouched, exactly where it always was. Follow that surviving question to its end, because it leads somewhere definite, and the channel does not deal in agnosticism. Something has always existed. The alternative, absolute nothing producing everything, is not merely improbable, but incoherent. That something is the foundation on which closed timelike curves and density matrices and fixed point theorems are all merely patterns. What can we say about it? We can reason from the product to the maker, the way you reason from a precise instrument to the intelligence that machined it. The foundation must be uncaused, because the chain of dependent things cannot regress forever. An infinite chain of borrowers with no original lender never produces a single loan. And yet, here we are, the loan made. So the chain terminates in something that does not borrow its existence from anything else, something eternal and self-sufficient. That something must be capable of grounding the precise mathematical order we find at every level, which means it is not the brute, formless, unconscious matter the secular reading requires, because unconscious matter has no power to prefer one precise configuration over the infinite alternatives. And the configurations we find are precise. Preference among possibilities is the mark of will. The capacity to ground mathematical order is the mark of mind. An uncaused, eternal, intelligent cause, possessed of will and knowledge and power. This is not a god of the gaps, invoked because we ran out of physics. It is the rational terminus of following the physics honestly all the way to its edge, and then asking the one question physics is structurally unable to answer. Many sincere and intelligent people stop short of this conclusion, and they are not mocked here. The questions are genuinely hard, and the honest seeker is owed respect. But the argument, examined without flinching, lands where it lands. The evidence points one direction. Let me bring this exploration to a close. We began with a traveller stepping out decades before his birth, raising his hand against his own grandfather, and a classical universe breaking on the contradiction. We followed the geometry that makes such a journey conceivable, Van Stockham's spinning cylinder in 1937, Gödel's rotating universe in 1949, with its declaration that travel into the past is theoretically possible. Tipler's sharp threshold, the wormhole time machine of Morris, Thorne and Yurtsever, and Hawking's chronology protection standing guard with a conjecture he could not prove. We watched David Deutsch in 1991 rewrite the journey in the language of quantum states, his fixed-point condition finding always a self-consistent density matrix, the grandfather-qubit settling at exactly 1/2. Your past rendered as a 50-50 balance of the self who acts and the self who fails. We saw the maximum entropy rule added by hand, the PSPACE computational power that should make us wary, the objections of nonlinearity and non-uniqueness and discontinuity, the rival P-CTC model that disagrees with Deutsch and with itself, and the implications of determinism and many worlds and quantum immortality, each reaching past what the equations can carry. And then we tested the claims built on all of it, and found that the loop does not remove the first cause, but presupposes it, that the resolution does not abolish order, but imposes it, that the 50-50 self does not dissolve the soul, but is contemplated by it. The mathematics is sound, the mathematics is beautiful, and the mathematics does not explain why there is a structured reality for the mathematics to be true of. That question survives every loop. A self-consistent cycle, examined honestly, is not the absence of a cause. It is among the strongest evidence that a cause with knowledge and will stands behind the whole precise, ordered thing. The evidence points to an intelligent first cause, eternal and uncaused, and the loop in time, far from erasing that cause, only sharpens the question to which that cause is the answer. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. Deutsch's equation found a fixed point and balanced the paradox. And in doing so, it laid bare the one thing it could never balance: the simple, stubborn fact that there is something here at all, ordered enough to fold time and to be understood by the minds folding it. The loop closes, the equation balances, and the deeper question, the only one that finally matters, stands exactly where it stood before you ever stepped into the machine. Good night.